welcome back to another episode of Pollys Introduction to Computer Network. And did I miss anyone here in my greetings? Oh, I missed Kevin and Oscar. Okay, good afternoon to both of you as well. And guys, you know what? This is week 14, which means we are only 3 weeks away from summer. All right, isn't it? But I understand, yeah. There are still 3 weeks to go, including this week. And we do have quite a few assignments this week, okay? But allow me to explain. The PA is just the last PA. If you get by PA 7 and 8, all right, then you should not have trouble doing PA 9. And we do have a lot of quizzes due by Saturday as well, but allow me to explain. The first 3 quizzes, they are substantial, but they are also straightforward. Last 4 quizzes, they are essentially trivial. They are just there to set stage for Polly to talk about a weird form of doing routing. Okay, that one is not exactly intuitive, understandable, but not intuitive. Okay, so Polly needs a few quizzes to set up the stage to explain the spirit of that routing algorithm. And then, I guess many of you are still wondering, right? When is the result of exam 2 is going to come out? They are going to come out tomorrow, 1 p.m. All right. And guys, bad news. Exam 3, the last exam, is coming up just about 2 weeks from now. But you know what? Good news is that after that, summer is right there. All right? And you have worked so hard the past 13 weeks. Okay? Just hanging there for a couple more weeks, maybe 3 weeks. All right? Yeah. Hi, David, Cedric, Franklin, Mark, and Minglen. The topics this week, okay, is going to be in 2 parts. First is to finish chapter 4, and the other is to start chapter 5. Okay, and we'll talk about this thing called generalized forwarding to close chapter 4. So this is the modern form of forwarding. And in this video coming up, 4.5 minutes, the first part is going to show you how more general the forwarding is. You'll see an example with illustrations. Okay, and in this example, you will also see Polly using a term, flow table, in place of this term, forwarding table, we keep using for the traditional forwarding. Okay, so flow table is a way of calling that database in a way that's also more general as opposed to the traditional forwarding that only matches on the destination IP address. So 4.5 minutes. Last section in chapter 4, generalized forwarding and SDN. So in these SDN routers, okay, the way we're doing forwarding is actually different from the traditional one, therefore we call it the generalized forwarding. In traditional routing, if you still recall, in the data plane, when packet arrives, we look at the destination IP address and we try to match destination IP address to the prefix entries in the forwarding table. If we match one, what we essentially do is to forward the packet to the link interface indicated in the entry. Okay. So in the traditional forwarding, what we're doing in terms of matching, very specific, the destination address. What we're doing as an action is simply to forward the packet further. But in SDN routers in the data plane, the matching and actions are now a lot more general. This is the architecture of the modern routing, or SDN-based routing. Now the separation of data plane and control plane, this part is actually very similar to the traditional routing. Now, if you recall the overview of chapters 4, you should recognize in SDN, the control plane looked very different. Instead of having routing algorithms running on each individual routers, we now run the routing algorithm centrally on one or maybe a couple powerful machines. And these machines could be slightly far away from the routers in the network. Now, what's a bit similar though between SDN routing and the traditional routing is this. After route computation, we generate tables like this. Okay, this is similar to traditional routing, right? In the control plane of the traditional routing algorithm finish computation generates forwarding table, and we install forwarding table to the data plane of the traditional router. Now, in SDN, tables are generated as well from the routing algorithm computation, and we also install these tables to the data plane of the SDN routers. You see, the control plane to data plane connection there between SDN and traditional routing very similar. The only slight difference is this. In traditional routing, we call these the forwarding tables, but in SDN, we call them the flow tables. Okay, so each router there will be installed with these flow tables to handle packets coming in. And so the flow table, if we zoom in, it looks more like this in SDN. In traditional forwarding, we have what? Prefix, the first column, and the link interface, the second column. The actions being taken is very simple, matching prefix, and then forward to a link interface. So what we're doing is always forwarding in the traditional routing. But in SDN, these actions could be more general, okay? Not just forwarding. So calling it a forwarding table is a bit awkward. So instead, in SDN, we call it the flow table instead. And by flow, okay, SDN is actually referring to each of these entries, each of these rows in the table. That is also saying if packets coming into this router, okay, where multiple of them matching a particular header combination and therefore take the same action, they belong to the same flow. So each row here is a flow. Okay, so we have a table of many flows in a sense. So what I'm showing here is also an example. Packets could come in with the headers looking like this, the destination being 0100, source IP address being 1101. Okay. Now we need to go ahead and look up the flow table in this router, okay, and then determine it should go out on interface 2, arriving at this router next. Now in order to do that, there needs to be an entry, let's say this one here, okay, matching the destination and source address. So in the header column, okay, of this entry, there should be specification looking like this. D equals 0100, S equal 1101. Therefore, when this packet arrives, look up, we match this entry, and therefore take the action here. Now, forwarding to interface 2, the action there should look like this. Okay, so matching this packet to the combination of header fields and take the action. Now, in the meantime, we take the action, this thing here. Okay, for this entry, the counters, both the packet counter and the data byte counter will be added. So packet counter will be added by 1 for one packet. Data counter will be added by the size of the data here in the packet. Okay, so you see, header column here for matching purpose, last column here for action purpose, and counter here for management purpose. Yeah, so you see, inside the flow table, these entries are more general. Okay, in first, the fields we match. Okay, and there's also action, which is similar to the traditional forwarding, but in traditional forwarding, there's only one kind of action, forward. And there's also a counter that you can keep for management purpose. But these are not the only attributes you specify in a flow table entry. So next video, also about 4.5 minutes, you will see a more detailed description of what the flow entries will look like. There's one more attribute called priority to break tie in case a packet matches multiple entries. And towards the end of the video, you will see also specific examples of these flow table entries. To put in simpler words, we take a combination of these header fields with specific values, and we define that as a pattern, okay, for a flow. So whenever there is a packet coming in, the SDN router is essentially determining which flow the packet belongs to, because that flow entry is going to tell the SDN router how to handle the packet. That is called the generalized forwarding. So step number 1, the most important step. For each incoming packet, take the header. Try to match the various patterns, okay, in the flow table. If there's a matching entry, go to the action column, so that's step 2, and then handle the packet that way. It could be simply to forward the packet to the next router, or drop in the packet, or modify the packet, or send the packet to the remote controller. So that is usually for debugging purpose, by the way. And step 3, increment the counter so that we track number of packets matching to the flow, number of bytes, okay, matching to the flow. Now, priority. Yeah, so this is something that we have not yet talked about, the priority column. Okay, so the flow table should have actually 4 columns instead of 3. Let me explain why we need priority there. Yeah, these patterns, okay, in the flow table, some of these patterns could be more coarse-grained. Many of the packets might match the pattern. Some might be finer-grained. Okay, few packets will match the pattern. So if we have multiple patterns that are coarse-grained, chances is actually high that they overlap. Okay, therefore, for a packet incoming, that packet could potentially match to multiple patterns, multiple entries, and each entry specifies an action. So, which actions do we take then, right? So priority there, okay, is to specify which pattern carries a higher priority and which one carries less. So we could differentiate or break the tie among all the matching patterns. Which one should be taken priority? Therefore, we take the action, okay, in the prioritized entry. Okay, so priority there is to disambiguate all the matching entries. Now, in traditional forwarding, we don't need to specify a priority. Why? Traditional forwarding there is to do what? Prefix matching. We do have multiple prefixes existing in the forwarding table. So one packet could actually match to multiple prefixes. Then, you know what? In traditional forwarding, we are also doing the longest prefix matching. That actually breaks the tie naturally, because there's only going to be one longest prefix. Okay? Unlike in SDN, we could have multiple patterns, and the patterns are now general, right? It's not always prefix, so you cannot use the lengths to break the tie. So we have a specific priority field there to break the tie. Okay, so the forward table in the router, 4 column, and it defines how the SDN handles a packet. It defines the match and action rules. To be more concrete, let's look into 3 examples. Now, in all 3 examples, we look at the source address and the destination address header fields. Now, in example number 1, we don't want to match the source address being 1.2. something. Okay, so the asterisk here meant wildcard, meaning arbitrary values for the last 2 octets. Destination address must match 3.4.5 for the first 3 octets, and then it doesn't matter what the 4th octet is. Now, all packets matching this pattern will be dropped. In second example, source can be anything, but destination address needs to match 3.4. something, and then we forward all those packets to interface 2. Third entry, 10.1.2.3, as long as the source IP address is exactly this, we send the packet back to the remote controller. So 3 examples, you get a rough feeling. Now, let me come back here. I have not yet explained what OpenFlow means. This is the data plane abstraction for SDN routers, all right. Okay, what does OpenFlow mean? OpenFlow, capital O, capital F. It's a very specific term. It is the protocol defined for communication between the data plane router to the control plane remote controller. So the remote controller installing forwarding table using the OpenFlow protocol. Alright, so from the video you see that not only the matching rules can have a variety, the actions can also come with varieties. Even for the counters, right? You can count the packets as well as bytes. Now, next video, short, 2.5 minutes, that is just to let you see how extensive the variety is to specify the rules. Pretty much all the packet headers can be used. With the generalized forwarding explained, now let's go back to this notion, the flow table. This is one of the most important things in SDN's data plane. Recall early slide, flow table consists of a number of columns, and you now know it should be 4 columns to be exact. There's this column, priority, and we just ignore that here, as it's not often used in SDN anyway. The stats column is essentially the counter column in the early slide. There are 2 counters, we know, one counting bytes and one counting packets. Action column, 4 classes of actions. One can forward the packet to an outgoing interface. One can forward the packet to the remote controller. One can drop a packet as an action. One can also change the content of the packet as an action as well. So all these straightforward. Now, this column here, very complex. Okay. It really depends on the header fields you're using and the values you're using. So the entries, the rule column part of the entries can be very diverse. So the rule column here, in the early side is also called a header column. The reason it's called the header column is we're using the header fields essentially to compose these rules. In the 3 examples we just walked through, we're using the source and the destination address. These are the header fields in the network layer packet header. One can use other fields in the network layer header for the rule. One can also use fields in the transport layer header, such as the source port number, destination port number, to compose the rule. One can also use the link layer header fields to compose the rule. What's even more amusing is this. These are all fields in the packet headers. One can also use fields that's outside of the packet headers. This is called the switch port. What this means is the packets coming into the router through a particular incoming port. So that's what the switch port meant, the incoming port, the incoming interface. So how we forward the packet can also depend on where they come in from. So that's also why in this slide we refrain from calling this column the header column, because we do have a field that's not necessarily a packet header. So we call them rules in general. Okay, now you see. SDN router is a way more general machine. The kind of rules you can specify for the matching entries is just so many combinations. Very intensive. Let me say it again. And next video is to show you a few examples. And so you see that SDN router can be a router, of course. It can be a router that works just like the traditional router. It can be also a machine that serves an application layer purpose, for example, doing firewall. It can also work like a lower level, a layer 2, the link layer switch. Very interesting. Let's take a look at how diverse these rules can be, again through a number of examples. First is the destination-based forwarding. Now this is essentially the traditional forwarding, where we look at the destination address. So if you have a packet, the header, the destination field says 51.6.0.8. Now we forward that packet to the output port number 6. So you see here, the SDN router can actually emulate the behavior of a traditional router. And the flow table there is actually a very general form of the forwarding table. The second and the third example are there to serve security purpose, to set up firewall entries. So let's take a look at what they're doing. First one is actually trying to match the destination port number header field. So if the packet's destination port number is 22, we drop the packet. The second one is actually matching the source address header field. If the packet source is 128.119.1.1, then we also drop the packet. So you see, dropping packet, definitely, something that the firewall does. Now, why blocking packet going to port 22? Why blocking packet coming from a particular IP address? Allow me to explain. So port 22 is also the port number of the SSH server. So this is the server that you contact to every time you try to log into the workstation. So after you type in SSH, what do you do next? You give the username, right? And then the server is going to prompt you for password. The hackers around the world is trying to SSH into the machines around the world. Using what? A mean or a root username, and guessing the passwords for the root or a mean. Now, if they guess the password right, then they get into the workstation and they get to play around and set things up or change things or encrypt your PA assignments and then send you ransom emails. So blocking packets to port 22 is to block any logging request to port ep22. Therefore, SSH is disabled, okay, on the machines behind this firewall. Second entry there. Okay, so this is actually more to try to prevent this attack, DOS attack, denial of service attack. You see, yeah, system admins around the world, especially those who are experienced, they will go up to these websites where the system admins share, okay, IP addresses of zombie machines. So if one day a hacker hacks through the workstation, okay, and take over the workstation, 140.112.42.161 is going to be a zombie IP address. Okay? So the experienced system admin, okay, after looking up the website displaying all these zombie IP addresses, can set up these entries, okay, with the zombie IPs here. That would actually block all the zombie incoming traffic if a higher level hacker comes in, okay, and asks all the zombie machines to issue, for example, login requests. Okay, then our machine is going to under attack. So experienced admin setting up these entries ahead of time will prevent us from the DOS attack. And this attack is also called the SSH brute force attack. Yeah, guessing the password by repeatedly trying, that is a brute force attack. Example number 4, destination-based layer 2 forwarding. I know we have not yet talked about the link layer protocols, aka the layer 2 protocols. So this entry here could sound a bit fuzzy to you guys. Now, so let me tell you ahead of time what the purpose of the entry is. So with this entry, the SDN router is emulating the behavior of a layer 2 switch, of a Ethernet switch. I think we've seen something like that when we're talking about the subnet, right? Within a subnet, there are these interfaces that are connected, but the connection is there through a switch, through a link layer switch, okay, or an Ethernet switch. So you see, from one machine, this network interface could have a frame passing through and coming to the link layer switch. Now, this link layer switch, we need to look at the destination address, but the link layer destination address to decide how to forward it further so that it reaches other interfaces on the same subnet. Okay, so that is the use of the switch there. So you see why. This entry here is looking at the destination address and the link layer. That is also called the MAC address, and it looks very different from the IP address. So if this packet comes in matching this link layer address, then that's forwarded to output port 3. Right? So that is the idea. All right, and that takes us to quiz 36. This is yet another example, but you'll be asked to guess, okay, what these 2 entries are for. So these are 2 flow entries, right, in the flow table, and they work in combination between each other. So let's take a look at the first entry first. So you see, first entry says this: if a packet comes in and the source IP address is 10.0.0.1, port number being 52391, then we take these actions, changing the source IP address to 140.112.42.161, and this is a global IP address belonging to the EE department. Okay. And then the source port number is also changed, 11999. Okay, so this is the first entry. Second entry says, oh, this time check the destination address, destination port, in case the destination is 140.112.42.161. Hey, exactly this address we've changed previously to a packet's source IP address. And the destination is 11999. Exactly this. Then we do also these things. Change the destination back to 10.0.0.1 and the destination port back to 52391. Exactly these. So these 2 entries are here to match packets coming from this guy, from this port, to this other IP address, this port. And it's also looking for packets coming in, right, with the destination, this IP address, this port number, and change it back to this IP and port number. All right, so let's go to the score. Oops. Quiz 36. Oh, wow. Okay. Yeah, so many of you have already typed up the solution before Polly put out the quiz slide. Okay, but you know what? You guys are all right. Yeah, it is Nat, right? Quite obvious. And Gladys, he is the first. Okay, I see that there's a lot of love from the teammates. Very good. As I guessed, yeah, the quiz is straightforward. Nat. Great. And so, yeah, that's have it done with. Good. And then come back to the lecture. So next video here, the first half you will hear exactly Polly saying that SDN router is in fact a very, very powerful general packet processor. It's not just a router. And you can imagine why these SDN routers are expensive. They can be used in a very flexible way, much like a general PC. So, first part of the video is that. Second part of this video is this. So far we've talked about is just the flow table, okay, of an individual router. If you recall, the modern routing works this way. There's a centralized, right, remote controller doing the route computation, route configuration, and install flow tables into all the routers within the domain. Okay, so second half is going to give you an example of such a network that runs SDN routing. With those examples, you see how diverse these rules can be. But you probably also see how powerful these SDN routers can be, right? It can emulate the traditional forwarding, just like the traditional routers. It can do longest prefix match, okay, and forward it out on a particular interface. It emulates also a link layer switch, so matching on the destination MAC address and then forward the packet further. It emulates also firewalls, okay, by looking up the source IP address or destination port number and then dropping the packet or allowing the packets. Yeah. One additional emulation SDN can do is this, netbox. Because what? One of the actions allowed in generalized forwarding is this, changing the content in the packet. So netbox there, okay, when there's packet coming from the local network, before you send it out, what do? We replace the source address and the source port number. So we could rewrite, okay, specific address and port number, okay, according to the need. So SDN, okay, is a very general machine that unifies, okay, a number of these different devices that we need, okay, running from the network layer and below. The last example is actually to go beyond one single SDN router to have multiple of them and forming a network like this. Okay, so you see here, this network, okay, is composed of 3 SDN routers, S1, S2, and S3. And then for each of these, talk to the controller through the OpenFlow protocol. Right? So this controller here sometimes being also called the OpenFlow controller. Just like the SDN routers, okay, some of them will actually call them the OpenFlow routers. The scenario is this: let's send packets from H5 and H6 here and here, okay, from subnet 10.3 to H3 and H4, H3, H4, subnet 10.2, okay, but through a very specific route, okay, from S3 here through S1 and then reaching S2. So yeah, we want this path. Now, the reason we want to do this in SDN is this. In traditional routing, the routing algorithm usually gives you this, okay, if you want to send data from 10.3 subnet to 10.3 subnet, because this is only one hop. Okay, this is the shortest path. Traditional routing does not provide you the flexibility of manually configure a specific route. But hey, luckily we have the OpenFlow controller. So OpenFlow controller can actually manually configure these flow table entries to S1, S2, and S3 to allow a specific path, S3, S1, S2. And these entries will look like this. Okay, inside S3, The flow entry will look like this. Source being from 10.3, destination being to 10.2. That's for the packet on interface 3 here. Now the entry in S1, this router at the bottom, will look like this. If the increased port is 1, so this is incoming port number being 1. Source 10.3, destination 10.2, that's forwarded down this interface 4. And then we manually configure S2 flow entry looking like this. Increased port being 2. Yeah, so packet is definitely coming in from here. Now, we need to separate the traffic so that it goes to H3 and H4 correspondingly. All right, so these are different IP addresses. So if we match more exact, the destination address being 10.2.0.3, then go on interface 3. So there I got this one. On the other hand, if it's 0.4, then forwarded on interface 4, therefore reaching H4. So open flow, really nice and flexible. So something to add is just here. Traditional routing implements a routing algorithm. You know what? Yeah, the controller can actually run a combination of manual configuration plus the routing algorithm. So it's a lot better, a lot more configurable, a lot more flexible than the traditional routing. All right, so now let's exercise and play God, okay, who's doing the configuration here, okay, at the OpenFlow controller, right? So you see that quiz 37, the network is just the same as the example in the video. So you see that we have 3 domains, A, B, and C. Each domain there's a big router, router A, router B, and router C. So in domain A, we see the 10.3 network, right? And inside this network, there are 2 subnets, 10.3.1 subnet and 10.3.2 subnet. Okay. And inside router A, we see there's an entry in the flow table that matches on the source IP address, as long as it's 10.3. something something, match. And it needs to match the destination address. As long as it's 10.2. something something, then do this. The action says, forward it through port number 3, which is downwards this way. Okay, so this is how you read the example. Q1 asks first, which way would traffic from H6 to H4 go? Where's H6? Up here. 10.3.1.1, and then H4 down here, 10.2.2.1. So by reading A's forwarding table, B's forwarding table, and C's, I'm sorry, not forwarding table, flow table, can you tell? Okay, what is the path, okay, this packet will traverse? Okay, Q2, suppose H6 here, okay, needs to send traffic directly to H4 such that the delay is the shortest. Okay, hey, as Polly explained, traffic coming from 10.3. something something is going to go down this way, right? But between H6 and H4, what is the shortest way, right? As human beings, we can see it's obviously this. This is more direct. Okay, so can you reconfigure the flow table in A, B, C? Could you change the tables of router ABC such that the traffic from H6 to H4 will go straight this way? All right. Oh, and this one might be a little bit tricky. So how about I give you 4 minutes time, and let's go to the score W14 quiz 37 channel, which you see already one of the students posted. Okay. All right. Oh, okay. Oscar is still changing, so it might not be that straightforward. So 4 minutes, and let's go. Yeah, I think you guys have got it, right? So what we need to do is to change here, isn't it? Yeah, so instead of forwarding it to interface 3, forward it to interface 4. Okay, this way, traffic coming from 10.3 to 10.2 will be enforced going this way. We also need to change this table, don't we? Because both of these entries matches on ingress port 2. The packets will be coming from ingress port 1. And since the goal is to make sure that the packet arrive at H6, which is 10.2.2.1, so we change this entry by changing it to, ingress port 1. And forward to interface 4, that would lead H4's traffic to, H6 traffic to H4. Good? Yeah, so you've got the idea. And now we can start chapter 5, okay? So this coming video is very short, just a quick review of the 2 functionalities in the network layer. And we focus on the routing that is in the control plane. And just like forwarding, we have the traditional forwarding and the modern forwarding in the control plane. We also have the traditional routing and the modern routing. The traditional one is more distributed, autonomous of all the routers, but the modern one is more centralized, power control. There's one God controlling all the routers. Okay, 2 minutes. Let's go real fast through 5.1, the introduction. Again, network layer, we run 2 major functions, forwarding and routing. Forwarding is about moving packets real fast from one router to another. Routing, however, is for each router to generate this forwarding table or flow table, or to determine the routes for the packets to move, from one to another router. So, in chapter 5, we focus on the control plane here. The 2 models, for route computation are these: the traditional routing versus the SDN routing. In the traditional routing, each router implements part of these routing algorithms, and so the route computation is somewhat distributed, and the routers work collaboratively to come up with the best routes. So there's per router control plane doing the route computation. But in SDN, the route computation is more centralized, running on powerful machines, and also somewhat distant from the physical routers. So centrally controlled. And this control is called the remote controller, as they are being physically distant from the router. More specifically, in traditional routing, the routing algorithm is implemented and running on each of these routers, and they'll be interacting with each other to generate the best routes, therefore coming up with the forwarding tables. So in the data plane, there's this forwarding table in the data plane. The control plane there runs the routing algorithm, and together they generate the forwarding table and forward it and installed in the data plane. Now, the modern routing, the SDN routing, works this way. There's going to be a remote controller there, doing all the computation and then interacting with the local control agent to install these forwarding tables, or more precisely, flow tables. So router, data plane here, having these control agent, and then at the control plane, we have powerful machines running the remote controller. Remote controller interacting with the CA, setting up these flow tables. All right, so a quick review. Next, the routing. So you can imagine that on the internet there are these routing protocols, that's operating, working. to allow packets to go from one to another host. Okay. And so this next video, a little bit long, 5 minutes, is to tell what is the purpose of these routing protocol. Okay. In a nutshell, if you think of these routers, individual routers, as an individual vertex in a graph, and the links connecting the routers as an edge on a graph, okay, you see that a network is essentially a graph. Okay. On a graph, you can try to run algorithms such that you find a shortest route, shortest path from one vertex to another. Yeah, that is the goal of finding the shortest path on a graph. That is also the goal of routing protocols on the internet. Now the core of chapter 5, the routing algorithms, or the routing protocols. So a good routing protocol there should be able to identify good paths or good routes from the sending host to the receiving host through this network of interconnected routers in the middle. So that is essentially trying to come up with a path. Okay? A path is a sequence of routers, one connected to another, and connecting the initial source to the final destination, okay, such that this path here is the least in cost, so we pay the least, or the delay is the shortest, or the promised bandwidth there is the highest, therefore the congestion level will be the lowest. Okay, so finding a good path, that is the goal of a good routing protocol or routing algorithm. It's also one of the top 10 problems in computer network, just like reliable data transfer, just like congestion control. In the next couple slides, Polly is going to introduce this new term called graph. A network, okay, of routers interconnected by links is a graph. So let's focus on the network in the middle here. What you see is that we have router U, router V, W, X, Y, Z. So we have a set of routers, okay, and there are 6 of them. Now between the routers, we have also links. So link UV here connects router U and router V. Similarly, UX here connects router U and router X. VX, V here, X here. Yeah, VX is the link connecting router V and router X. Link VW, connecting router V and router W. So you see we can go over all the links defined here, and this forms the set of links interconnecting the routers. And coincidentally, a graph is also defined in a very, very similar way. A graph consists of the set of nodes and the set of edges interconnecting the nodes. So N here stands for nodes, and here, E here stands for edge. So if you consider the routers being nodes, yeah, so the set of router here is the N here. If you consider links being the edges, then E here is the set of the edges. With the set of nodes, set of edges interconnecting the nodes, we do have a graph. So a network here is also a graph. And such an abstraction is really, really convenient later on when we're introducing the algorithm. It could also be useful when we're talking about other kinds of networks. So for example, in the application layer, chapter 2, for P2P, okay, you see there, okay, there are peers here, there, all around the internet. And we establish connections between the peers, right? So we could do what? P2P communication. So if you consider each of these peers as a node, and these TCP connections or UDP connections connecting the peers as an edge, there, you also have a graph. You also have a P2P network. And you can also run a routing algorithm, okay, on a P2P network, if you think about it. And now we can talk about this other thing, okay, it's called the link cost. So associated with each link, okay, on a graph like this, you see a number nearby, that is the link cost. To denote the cost of a link connecting router X to X prime, we use this notation, CXX prime. So CWZ, connecting router W to router Z, a link here, yeah, the cost of that link is 5. Right? That cost, okay, can be set in a variety of ways. For example, set it as the inverse of the bandwidth available. You can also set it to the inverse of the traffic level. You could also set it simply to a constant, such as 1. Every link costs the same, 1. Okay. So that is link cost. cost of a path, okay, is essentially also very simple. From the source x1 to the destination xp, it's the sum, okay, of all the link costs connecting from the source to each of the routers along the path, all the way till the destination. So it's the sum of the costs from the source to the first hub router, x2, c x1 x2, plus c, the first router to the second router, x2 x3, and so on and so forth until the last router, xp minus 1, to the final destination. Okay. So let me use an example. Let's say traversing from U to Z, and we take this path. Yeah. The cost of the path will then be adding 2 to 3 to 5, and that will be 10 here. All right. So the goal of routing algorithm is essentially to find the least cost path, okay, between a pair of nodes, okay, from source to destination. All right, so that is essentially what routing protocol wants to do as well. And tomorrow morning, Polly will start showing you the 2 routing algorithms that are commonly used on internet routing. With that said, I say goodbye. That's all the time we have today. Okay, see you tomorrow.